Hi guys, I'm back and we're going to talk about more about water. We're going to talk about condensation this time. So, without further ado, here we go. Okay, so condensation is basically just the opposite process of evaporation. So, we learned that evaporation is this process that takes water from the environment and takes water and takes energy from the environment and turns that liquid form of water into a gaseous form of water that then floats around in the atmosphere. So condensation takes that water and takes that energy and converts it the opposite way. It turns it back into liquid, releases the energy as it does that, and that liquid can fall to the ground as rain. It can freeze and fall to the ground as snow or sleet or hail, or it can just hang out in the atmosphere in little water droplets in the form of clouds. And sometimes those clouds just re-evaporate into the atmosphere and never end up as precipitation. And sometimes they do. But the process of condensation is the kind of turning back of the gas form of water into the liquid form of water. And as we said, it releases that heat that's called the latent heat. And it releases that heat or energy that was used to get the water to evaporate in the first place. The water molecule in the vapor form and the gas form held that energy as it was zipping around in the atmosphere. And then when it's done zipping around and it's ready to be more still again in the form of liquid, it releases that energy back to the environment, and that can actually heat the environment up. That can actually warm the environment up a little bit. Okay, so when does condensation occur? Well, condensation occurs when the air arrives at what's called the dew point temperature. And somewhat confusingly, this is actually not a specific temperature, but different air masses have different dew point temperatures. And the dew point temperature is essentially the temperature of a particular air mass when that air mass becomes saturated with water, or we could say when that particular air mass reaches 100% relative humidity, or we could say when that air mass has its water holding capacity completely maxed out or completely filled up. And so it's not a particular temperature, again, because different temperature airs have different water holding capacities. They have different capacity to hold on to water. And then different air masses also have a different water content. So it's this complex dance between the temperature and the water content. And that's going to drive what a particular dew point temperature of an air mass will be. So for example, this is the dew point temperature that was collected back in the summer of 2002, but it's kind of a representative summertime average-ish dew point temperature across different parts of the United States. The different colors represent different temperatures, and the warmer temperatures in the reds are somewhere on the range of like 75 to 79 degrees Fahrenheit. And in the locations that are in red, like in places like Florida, like Louisiana, the air does not have to drop down to be very cold to get to a point where it reaches its dew point temperature, and the water in the air will start to condense, form clouds, and potentially lead to rain. So in the summertime, these areas that are pretty hot will have a lot of moisture in them. And even though it's pretty hot, there may be pretty consistent and regular rainfall. In other parts of the country, like in the Rocky Mountains, like in other parts of the Great Basin, in the Sierra Nevada, where the colors are blue, that's the coldest dew point temperatures on here. It shows that the dew point temperature is in the range of 31 to 34 degrees, which is close to the freezing point, 32 degrees. So in those locations, there's so little moisture in the air that the air would have to drop all the way down to nearly freezing. The water holding capacity of the air would have to get so small that even a very small amount of moisture would start to overflow the capacity of that air mass to hold onto moisture for us to get rain. And so in these parts of the country, we have much, much drier conditions, very different looking landscapes as a result of the different humidities in the atmosphere. And so again, the dew point temperature is an interesting concept, but it's not a particular temperature. It depends on the conditions of the atmosphere. So if we want condensation to occur, as we just said, we have to reach the dew point temperature, which is the same thing as saying the air has to be saturated, which is the same thing as saying that the air has to be maxed out in its water holding capacity or at 100% relative humidity. And this can happen in two ways. One is that we can evaporate more water into the air. So we can actually pump more water into the air, and then we can start to max out the air's capacity to hold water in that way. So like if an air mass is sitting over a lake or a stream or the ocean for an amount of time, it might pull more moisture into the air that way. But more commonly, what we see in the environment is that water starts to come out of the air as a result of the water holding capacity of that air shrinking. So the container that the water is in, you can think of it, is shrinking down, and then the water starts to spill out of the container because the container is getting smaller and smaller. So the air cools down until it hits the dew point temperature, and then the water starts to squeeze out. So I like to think about this as like if you had a little plastic water bottle and all the water was in the bottle can hold all the water, and then you squeeze the bottle and you make it smaller and smaller. That's like what happens when the air gets colder and colder, and then eventually the water will start to come out of the bottle. So that's what happens when the air is getting colder and the water holding capacity is dropping. And in the environment, this is the normal catalyst for condensation. So here's some different pictures of where condensation is happening. And before we get into these, I want to mention one more thing, which is necessary for condensation to occur. And that is that there needs to be some sort of surface on which the water vapor can bond to start to form a water droplet. And this particular surface is called a condensation nuclei. So nuclei is like the center of something. This is the center surface piece onto which the liquid water can start to bond. And so this might be like something that's so small that we can't see it with our naked eye, like a really fine piece of dust or pollen or salt that's in the air, or it could be a mug or a shower door or our windshield on our car or the grass on the ground. And so these are all surfaces onto which water can bond. So in all these examples that I have here, first of all is like a frosty beer. And the reason that the beer is frosty is that the beer itself was refrigerated, it was cold, then we poured it into this mug. And so now as air from the room comes up to the mug, the air is being cooled down. The energy is being absorbed into the beer because the beer is colder. The air in the room is cooling down, and it's cooling down so much that all of a sudden it can't hold the moisture that it was previously holding it anymore. And that moisture starts to come out of the air and beat up and condense on the outside of the beer mug. So that's why you need like a coaster for like a cold beverage, but you don't need one for like your hot coffee in the morning. Here's like a shower door or like a mirror in the bathroom. The air that comes out of the shower and the water that comes out of the shower is obviously very hot. And then that hot, humid air moves over to the mirror. The mirror is colder. The mirror cools down the air that was holding all that moisture from the shower. And then that air can no longer hold all the moisture and it starts to beat up and condense on the mirror. And then of course, this happens at night in the form of dew that occurs all over like the ground and the grass. And so in this case, the temperature of the air just cools down at night enough until it can no longer maybe hold all the moisture that it could have evaporated off the landscape during the day. And then that moisture starts to beat up on the ground surface in the form of dew. So these are all examples of condensation. And of course, condensation can also happen in little droplets in the air as well. Okay, so when we're thinking about this idea of changes in air temperature leading to relative humidity. I just want to give you a little visual that might help you understand how this process works. So first of all, I have these different vertical bars here that represent the WHC, the water holding capacity of the air at different times of day when the temperature is different. So of course, the air is not like a rectangle, but you can just imagine there's a certain amount of capacity for the air to hold moisture. And if we could kind of try to quantify that, we could show it by these different spaces. So at 9 a.m. in the morning, maybe it's 70 degrees Fahrenheit and we have a certain water holding capacity. Then later on in the afternoon, after the sun has been shining down and pumping energy into this environment for a period of time, the water holding capacity expands. It gets taller because the temperature is higher. And then at night, after the sun goes away, that energy is no longer there. It's being lost from the ground, lost to space, lost to other objects in the environment, and the water holding capacity shrinks all the way past the capacity in the morning to an even lower capacity as the temperature drops farther at night. So we have these different water holding capacities that represent different temperatures. Okay, then we could use this little textured blue diagrams to show the amount of actual water content that was held in this air mass. And so the water content might be very consistent throughout the day. It doesn't change throughout the day in this particular environment, in this particular example. But how full the air is, the relative humidity of the air does change. So in this example over here, it might look like the air is about 80% full. So it would have a relative humidity of about 80%. And at that point, we would not expect to see condensation taking place. Then during the afternoon, in this middle picture, the water holding capacity expands. So even though there's still the same amount of water content in the air is now not as full as it was before. So it might have a lower water holding capacity. Maybe it's like 60 or 65%. And then at nighttime, the water holding capacity drops back down and then even farther. And it would get to a point where the water holding capacity now is maybe lower or at least equal with the water content. And so now we would start to see condensation take place in the form of dew, in the form of cloud formation, because now the water does not have the energetic capacity to continue to hold on to all that moisture. So it's not because more moisture showed up at night, it's just because the water holding capacity is changing as temperature is changing. And this is the kind of thing that leads to condensation. And as long as there's a surface around in the form of the ground, in the form of dust or pollen or salt or other things in the sky, then we'll see condensation take place. Okay, so here's just examples of condensation taking place in smoke, along smoke from fires. So when we see smoke after fires, a lot of that is particulate matter that is coming off the like incomplete combustion of like trees and other things that are burning. But a lot of it's just like water that's condensing on all those extra condensation nuclei that are put up into the atmosphere. Smog is the same thing down here in Los Angeles. We see all this like hazy smog looks a lot like fog, and that's because it's pretty similar. There's also particulate matter in the air and things like ozone and stuff that contribute to the pollution. But some of what we see is just water condensing on all the extra particulates that are being placed in the air. And then we see this kind of thing around like volcanoes and other things as well. So pollution, ash, salt, forest fires, all these things can add extra condensation nuclei to the atmosphere and make the condensation process more likely to occur. So as a little aside, you may have heard of cloud seeding before. So cloud seeding is basically the deliberate treatment of clouds, or the deliberate increase in the number of condensation nuclei that are in the air, with the hope that that will lead to an increase in condensation. And the more condensation we have in the atmosphere, the more likely it is for precipitation to occur. So this can be done in a variety of ways, and it's done mostly experimentally in this day and age, although there are some areas that have pretty regular programs where they do this, including some like PG&E efforts in the area around Lake Almanor, which is the headwaters to the State Water Project and feeds a lot of hydropower dams and stuff. So there's an interest in having rain in our watershed. But what they do is they can send off little flares from the ground, from planes, and mostly it's silver iodide, which is a very, very tiny little object. It could also be salt or dry ice. And these act as a nucleation site or a surface of condensation nuclei onto which water can condense. And so we know the air still needs to be at 100% relative humidity for this to happen, but the more surfaces we have, the more likely and faster the condensation might happen, and the more likely we may be able to capture some precipitation in a watershed where this is being done. So again, this is done experimentally mostly in this day and age. Different groups like the University of Nevada, Reno and the DRI, the Desert Research Institute there, have some research projects. PG&E has been involved in some research projects with this. But so far, it seems like it may lead to an increase of about 8 to 15%, or it may lead to an 8 to 15% increase in precipitation, which I'm noticing there's a typo there. So anyway, kind of a far cry from what many people think of as these like chemtrails, where we're being poisoned by our government, which I have never seen any evidence to illustrate as true. But this is a kind of thing where we are putting things into the atmosphere to try to change the way the atmosphere behaves based on our understanding of science. So anyway, that's what cloud seeding is all about. Okay, the last thing I want to mention on the topic of condensation is that sometimes this condensation doesn't happen in clouds up in the air or in dew on the ground, but happens kind of in an in-between environment. And we call this fog. Fog is basically just a cloud that's on the ground. And there's two main types of fog that take place. The first type is called radiation fog or ground fog. And this happens when at nighttime, usually when the sun goes down, the sun is no longer heating up the ground, it's no longer heating up the air, and the air, particularly the air that was being warmed by the ground surface, cools down significantly throughout the night. And as it cools down, the water holding capacity drops and the water starts to condense. And in particular, there's usually more particulates, dust and pollen and things like that relatively close to the ground, because a lot of these things are coming from the ground. So there's lots of surfaces onto which this condensation can occur. And so we can get this layer of cloudiness on the ground that we call radiation fog or ground fog. Radiation fog refers to like the loss of heat from the ground at night through radiation. So a lot of times when the sun comes up during the day and the sun heats up the air and heats up the ground, this moisture will re-evaporate into the air and then it will kind of like disappear. And we see this thing a lot around Quincy in the wintertime, where it'll be really foggy in the morning and then the fog will kind of like burn off as it re-evaporates into the air. Another type of fog happens, it's called advection fog, and advection is basically anytime we have movement kind of like laterally or horizontally in the environment. And so in this case, we have some sort of movement of air across the landscape that's pulling air of one temperature in contact with like land or water of a different temperature. And so normally this happens when warm, moist air moves over a cold surface. So like warm air, for instance, that's being heated up along the coast in the summer, comes in contact with like the cold ocean, and then there's lots of salt and lots of different condensation nuclei above the ground there. That would be a perfect place for fog to form. And so we see a lot of this fogginess along places like coastal California, where we have this diurnal, this daily movement of air in and out off the coast, over the ground, over the ocean. It's heating, it's cooling, and then that is kind of a perfect condition for, where fog can form. Okay, that's just an example of how this might happen. Okay, that's a good place to stop.